Today we're going to talk about the statistics part of the course, and mainly on the applications of central limit theorem and confidence intervals. Now, from last lecture, we talked about the statistical measures, and for any set of measurements has two important properties. And in order to describe a population, generally we talk about two important properties. They are the central or the typical values and the dispersion about that value. So very often we talk about the center, which measures the central tendency, as well as the dispersion, how widely spread is the population. Now we have a widespread population and we have a narrower spread population. So how do we describe the two populations using some measurements? And for the measure of central tendency, we use the mean in general. And by definition, the simple population mean is defined to be mu. Okay, where mu is just the simple average. If we happen to know all the values yi in the population for I from 1 to capital N. Capital N is the population size. However, we know that it is impossible to observe everything about the population. Otherwise, there's no statistics required. So in general, we want to draw a good representative sample from the population with a random sample of size small n. And the sample mean is defined to be y bar. Y bar is just the sample average by taking the average of the n observations. Okay, and another measure of central tendency is called the median. The median is just the midpoint of the data when arranging the data from smallest to the largest. The median is more appropriately used when the distribution is highly skewed, like the monthly salary of people in Hong Kong. And the mode is another measure of central tendency, and the mode represents the value that appears most often in a set of data. But in this course, we would simply focus on the mean, and we use the sample mean to make statistical inference about the unknown population mean, and that's what we are going to do. Now, for the measure of dispersion, very often we talk about the variance. The population variance is defined to be sigma square, denoted by sigma square, and this is the definition, which is the squared deviation from the mean, okay, of the n observations, and then we take the average, or this is also called the mean squared deviation from the population mean. But however, if the population mean is unknown, okay, and then we can estimate the population variance using the so-called the sample variance. But the sample variance is slightly different, and you can consider this as a definition. Now, this part is very similar to the population variance, except that we do not know every single values in the population. So we simply draw a random sample of size n, and we denote the observations by y1 up to yn, small n. Okay, and here the population mean mu is unknown, and therefore we estimate the population mean by the sample mean, and that's why we have this term. Now we have a sum of small n terms here, but the denominator, we simply divide this by n minus 1 instead of taking the average of these n square deviations. The rationale cannot be explained in this course, and please take this as a definition, and this is the definition of the sample variance. But basically, we will not be using any of the sample variance in this course. Other measures of dispersion include the standard deviation, which is just the square root of the variance. So we have the population standard deviation sigma, which is just the square root of sigma squared. And of course, we only consider the positive part of the square root. And similarly, the sample standard deviation, which is just the square root of the sample variance, denoted by S. Other measures of dispersion includes the range and the interquartile range, but in this course we will only focus on the variance. And the next thing we're going to talk about is the very important probability distribution called the normal distribution. And normal distribution is actually a very, very important distribution. How important it is. And in Germany, before they adopt the currency euro, they have their own currency called Deutschmark. And this is a picture of the 10 Deutschmark. And from 1989 through 2001, Gauss' portrait and a normal distribution curve were featured on the German 10 mark banknote. And here, right here, is the normal distribution, the plot of the normal distribution. And inside there is a formula read as fx equals to 1 over square root 2 pi sigma and exponent blah blah blah. And this is a normal distribution invented by Gauss, the Frederick Gauss, which is a very famous mathematician. And therefore, the normal distribution is also called a Gaussian distribution. So you can see how important the invention of the normal distribution is. So let's take a look at some basic properties of a normal distribution. And the normal distribution is the most important distribution in statistics. And we denote this by if a random variable y follows a normal distribution, we denote this by y tilde n and then mu sigma square. Okay, and that reads as y, the random variable y follows a normal distribution with mean mu and variance sigma square. And then the probability density function of y is given by this f of y equals to this. And this is the one that appears on the 10 Deutschmark as well. And this is what we call the probability density function. But you don't have to worry too much about the probability density function. For different values of mu and sigma square will produce different density function. For example, for the blue one here, it has mean 0, and variance 0.2, sigma square equals to 0.2. And for the red distribution, the red curve, okay, this is another normal distribution with mean 0 but variance 1. Remember, the variance is a measure of dispersion of the population. A wider spread distribution corresponds to a larger variance. Okay, so therefore the variance is 1 for the red curve and the variance is 0.2 for the blue curve. What about for this yellowish curve? We have a variance of 5, which is even much wider spread and is much flatter distribution. Okay, and one simple property about the distribution is that the area under each curve is 1. The area under each curve, each of the normal curve is 1. Okay, now other properties of the normal distribution, you can see that the normal curve is a bell-shaped curve. Well, it depends on how you call it a bell-shaped curve, okay? But this is not very important, but I don't know why every single textbook they put this down as the major property of a normal distribution. Other distribution also has a bell-shaped curve, but they are not normal distribution, okay? But all normal distribution, normal curve must be of bell shape. Okay, for example, whether this is a bell shape or not, okay, so it's up to your imagination. The second property is that we let the random variable y follows a normal distribution with mean mu and variance sigma square. And then we define a variable called z, okay, which is simply the mean, the random variable itself minus the mean of y and divided by the square root of the variance of y. This is just equivalent to what we call the standard score, okay? Y subtracted its mean and divided by the square root of the variance of the random variable y, okay? So, but what is the mean of y if we have this condition? The mean of y is known to be mu, and the variance of y is known to be sigma square. So basically, this z is a transformation of the variable y, which is given by y minus mu divided by sigma. Is a transformation of the random variable y, and we call this a z transformation, such that the transformed variable is known to follow a standard normal distribution. That means the normal distribution with mean 0 and variance 1 is what we call the standard normal distribution. Okay, now notice that this is the transformation. The random variable y minus its mean, the mean of y, and divided by the square root of the variance of y. Okay, so therefore we have y minus mu divided by sigma, and this is what we call the z transformation. Okay, so, and the third property of a normal distribution is that about 95% of the area is within the bounds mu plus or minus 2 standard deviation, 2 times sigma. So that means mu is here. Oh, let me talk about the fourth property first. The distribution is symmetric about the population mean. You can see that clearly from here. What is the meaning of symmetric? So if this is the mean 0, that means the left hand side is the mirror image of the right hand side of the mean. Okay, so that if you fold up the left hand side to the right hand side, the two will be identical. Okay, and that's what we call symmetric about the mean. So in other words, on the left, remember that the total area under the curve is 1 and the mean is here, and the distribution is symmetric about the mean. That means 50% of the observations, 50% of the area will be on the left hand side of the mean, and the other 50% of the area will be on the right hand side of the mean. Okay, so the third property says about 95% of the area is within the bounds mu plus or minus 2 standard deviation. That means we have the mean here for a normal distribution, and we have mu minus sigma, minus 1 standard deviation, minus 2 standard deviation. And also to the right hand side, we have mu plus 1 standard deviation and mu plus 2 standard deviation. So within 2 standard deviations from the mean, it says we have a total area of about 95%, and to be precise, that should be 95.4% for all normal distribution, irrespective of the mean and the standard deviation. The mean can be 0, 10, 20, minus 50, and the sigma can be 1, 0.2, 0.5, as long as within 2 standard deviation, that would be about 95%, and 68% within 1 standard deviation from the mean. That means from mu minus sigma to mu plus sigma, we have 68.2%. 68.2%. For 3 standard deviations, we have 99.7%. Okay, and the fifth property is that the smaller is the variance sigma square, the more peak is the distribution, like this one, sigma square equals to 0.2. Okay, the more peak is the distribution. The larger is the value of the variance, the flatter is the distribution. So we have a variance of 5 here. And also for the mean equals to minus 2, we have the green curve that with a center around at minus 2. Okay, so that is the properties of the normal distribution. Okay, now the normal distribution, we use the area to represent the probability. For example, if the random variable y follows a normal distribution with mean mu and variance sigma square, then we can find the distribution function of y given by probability that y will take up a value less than a equals to 5. For example, we can use the Microsoft Excel using the function equals norm.dist, and we simply input the quantity A as the first entry, the mean as the second, and the standard deviation as the third, and we type the logical argument to be true, that will give you the distribution function. For example, we have a normal distribution with mean mu equals to 10 and sigma equals to 0.5, and I would like to find the probability that a randomly selected subject from this population will have a y value less than 8, a equals to 8. That means we are looking for the area to the left hand side of A, and we call this phi, which is given by here. To find this probability y less than A, probability of y less than A, all we have to do is to make use of this argument norm dot dist to find the normal distribution function for y less than 8 based on a normal distribution with mean mu equals to 10 and standard deviation equals to 5. Then the Excel will give you a probability of 0.344578, 0.344578. Okay, what about if I want to find the probability of y greater than 12? Y greater than 12. Okay, using Excel will give you the area to the left of B, where B equals to 12. That is the white area. But in fact, we are looking for the blue shaded area here. That means, but notice that the total area under the curve must be 1. So we can simply find the white area and then subtract that by 1 to get the blue area. So therefore, in the Excel formula, you can simply type equals 1 minus norm.dist, and we have the input of B, which is 12, and the mean is 10, and the standard deviation 5, with a logical argument being true. Okay, notice that for the same normal distribution, A is 2 units away from the mean to the left hand side, and B is 2 units to the left, to the right of the mean. Okay, to the right of the mean. And notice that this, because they are symmetric, therefore this area should have the same area as this part. Okay, so they should have the same area, and that can be confirmed by using the Microsoft Excel. But notice that you're not supposed to find any normal probabilities in this course. You are not supposed to find any normal probabilities using Excel in this course, but I just mentioned it here. Oh, I mean, in this course, that means in the examination, of course. Okay, so what is the use of the normal distribution? Remember that in the scientific method, we also mentioned that in the mathematical modeling, we mentioned that we spherical cow. We make some simple assumptions so that the analysis can be made simple. For example, a study conducted in the United States on the heights of adult females and males suggested that the height of males in inches follows a normal distribution with mean 70 and variance 16, which is a square of 4, okay, with standard deviation 4. And the height of females follows a normal distribution with mean 65 and variance 3.5 square. Okay, now here is the histogram of the height of the females, and the blue one is the histogram of the height of the males. Okay, if someone asks you to compare the two distribution, then it would be easier if we have some quantitative measures. For example, we can compare the mean, whether in general male are taller than the females. We can compare the mean, whether the spread of the height of the males is greater than the spread of the height of the females. Then we can have some quantitative measures to compare. And very often, normal distribution is a good approximation to many real-life examples in general, just like the height of the females and the height of the males. Okay, and to find the normal probability, for example, what is the probability that y is less than 75, for example, for a male subject in the United States? Okay, probability of y less than 75, that means what is the probability that a randomly selected subject has a height less than 75, That means we would like to find the area to the left of 75. Okay, that is the meaning of the normal probability of y less than 75. That means what is the probability that a randomly selected subject from the population will have a height less than 75 inches. So we in general, a main assumption in statistics is that we assume that the population follows a normal distribution. Okay, exercise. Let x is a random variable. Let x be the height of males in the United States, as such that x follows a normal distribution with mean 70 and variance sigma square equals to 16. A male subject is randomly selected in the United States. Find the probability that x is less than 62.16 inches. Now, we simply use the Excel to calculate these probabilities, which is 0.025. And the formula is given here in red. And what is the probability that a randomly selected subject in the United States has a height greater than 71.6? And you can find this probability easily using this function, and it's found to be 0.3446 and so on. And what is the probability that a randomly selected subject will have a height that falls between 62.16 and 71.6? Then we can find this to be 0.6304. Maybe you can figure it out yourself how to compute this probability by drawing the histogram and to identify which region are we talking about here. Okay, and basically this is how you can find this probability using Excel. But basically what we would like to introduce here is that we have some very, very useful quantities, and they would be provided in the examination, and then you can imagine how important these quantities are. If we have a standard normal random variable, normally denoted by z because of the name of the z transformation. So if z follows a standard normal distribution with mean 0 and variance 1, then we have probability that z take on a value less than 1.96 would be 0.975. Okay, suppose we have a normal distribution here, standard normal distribution with mean 0, variance 1. Okay, and 1.96 is here, 1.96 to the left, the area of the curve to the left of 1.96, we have a total area of 0.975, and that means to the right hand side of 1.96 we have an area of 0.025. Okay, by symmetry, we have probability that a standard normal random variable will take on a value less than minus 1.96 here, and that area would be the same as the right hand side, which is 0.025. Okay, in other words, that means the probability that a standard normal random variable will fall between minus 1.96 and 1.96, and this probability would be 0.95. Okay, because we have 2.5% on the right hand side and 2.5% on the left hand side. Left hand side and right hand side. Okay, so the area in between would have an area of 95%, 0.95 here, from minus 1.96 to 1.96. okay, because we have 0.025 on the left hand side and 0.025 on the right hand side. Similarly, if we have 90% in the middle, then that quantity becomes minus 1.645. If we would like to have 95% probability in the middle, then that quantity becomes minus 1.96. And 95% would be most commonly used, and therefore sometimes 1.96 is also called the magic number in statistics, 1.96. And another quantity is 98% in the middle, 98% in the middle, then the quantile would be 2.326. Okay, now these three quantiles are particularly important that they will be provided in the examination, and you can find this in the last page of the exercise. You can find these quantiles in the last page of the exercise that I uploaded to the Moodle long time ago. Okay, now we take this for granted and assume that you have no problem with this three probability argument. Okay, you can find these probabilities easily from Excel. These three standard normal quantiles are commonly used in this course, as we will not go into the normal probability table. So we focus on three probability arguments, namely 90% standard normal 1.645, 95% standard normal random variable 1.96, and 98% 2.326 standard normal random variable. And this graph would help you to have a better understanding. 1.645, I would have 5% on the right hand side. Minus 1.645, I have 5% on the left hand side. So in between, I have a total of 90%. Okay. Okay, now we have a histogram for continuous data. This is the histogram for the Fisher's iris data. Now the disadvantage of using a histogram to plot the data is that different number of intervals will end up with different shapes of the histograms in general. Now, for example, we have this histogram for the Fisher's iris data, which is a very famous data set measuring the sepal length of a special species of iris, and they plot in this particular histogram. And what we're going to do, we assume that the data, the sepal width of the iris actually follows a normal distribution. But which normal distribution should we use to represent the distribution of the sepal width of the iris? Now, for example, the green one with mean 30 and sigma equals to 3.8, it touches the peak, it matches the peak very much, and the blue curve doesn't seem to fit the data very much. So in general, we use a normal distribution. We assume that the population follows a normal distribution. Okay, and the question is, if the parameters mu and sigma squared, the mean and the variance of the normal distribution are known, they are called the parameters of the distribution. Because if these quantities are known, then all the probabilities associated with the distribution can be obtained easily. If you go back to the earlier Excel demonstration, okay, if the mean and variance are known, we can input the mean and the variance. Then all the probabilities associated with this distribution can be obtained easily using Excel or by other means. Okay, that means if the parameters mu and sigma square are known, then all the probabilities associated with the distribution can be obtained easily. In other words, if the parameters mu and sigma square can be estimated accurately, then we know everything about the population. We know everything about the population. That means the distribution of X can be completely described by the two measures. The distribution of X can be completely described by the two measures. So when we talk about the sepal width of the iris, all we have to do is to mention the mean and the variance of the sepal width. Then everybody knows the distribution. Okay, and also we mentioned earlier about the Z transformation. We let Y follows a normal distribution with mean mu and variance sigma squared. And the transformed variable is denoted by Z, which is the random variable Y minus its mean, which is mu, and divided by the variance of this random variable Y, the variance of this random variable here, which is sigma. And this is a transformation of Y, and this is known as the Z transformation. And some important quantiles is 1.645 with 90%. That means 5% on the left tail and 5% on the right tail. And when the magic number 1.96 is used, that means we have 2.5% on the left-hand side and 2.5% on the right-hand side. And the area in between minus 1.96 and 1.96 is 95%. And also we have 1% on the left-hand side. The corresponding quantile is minus 2.326. And 1% on the right-hand side, the corresponding quantile is 2.326. And we have a total area of 0.98 in between these two numbers. Okay, so that is the brief introduction of the normal distribution. But how can we make use of the normal distribution to make statistical inference? How can we estimate the mean? And that's what we are going to talk about in the following. Okay, to have a better understanding of the situation, let me briefly explain the random variable sample mean. Very often in practice, when we draw a random sample, we can calculate the sample mean easily. But then that sample mean would be a constant, because we can only afford to draw one single sample with n observations. But however, statistics is something different. Okay, statistics means when we talk about the sample mean, okay, we talk about before we actually draw the sample. For example, let's consider a population with only 3 elements, 3 equally likely outcomes. That means, for example, the 3 outcomes are 2, 4, and 6, each with a probability of occurrence of being 1/3. Okay, 1/3. And notice that the mean of these 3 elements is 4. Okay, 2 plus 4 plus 6 equals to 12 divided by 3, so that the population mean is 4. Okay. Now, a random sample of n equals to 2 is to be drawn from the population with replacement. Okay, so what are the possible outcomes? The possible outcomes could be a 2 and a 2. Okay, 2 and a 2. And so that the sample mean equals to 2. Okay, if the first one drawn is 2, the second one drawn is 2, then we have a sample mean of 2. But the occurrence of this pattern is 1/9, because this is simply 1/3 times 1/3, that the first one is a 2 and the second one is a 2. And similarly, we can have the first one being a 2, the second one being a 4, or a first one being a 4 and the second one being a 2. That will contribute to the event of the sample mean equals to 3, and we have probability of 2/9. And the sample mean can be 4 based on these 3 possible outcomes: 4, 4, 2, 6, and 6, 2. With probability 3/9, it could be 5 and it could be 6. Okay, so therefore the sample mean before we actually observe the data, is a random variable that follows this particular distribution with sample mean equals to 2 with probability 1/9, sample mean equals to 3 with probability 2/9, sample mean equals to 4 with probability 3/9, sample mean equals to 5 with probability 2/9, and sample mean equals to 6 with probability 1/9. In other words, if we can repeat the experiment again and again and again, then you can see that the number of occurrences of the 5 possible sample means would be very much follow this distribution: 1/9, 2/9, 3/9, 2/9, and 1/9. Okay, and hence the sample mean y bar itself a random variable with this probability distribution, Okay, so when we talk about the sample mean being a random variable, that means before we actually draw the observations, statistically we have to make a full plan on the method of analysis before we draw the data. After drawing the data and then to decide to which method to be used would be a little bit ad hoc, and manipulation of data can be taken place easily. Okay, just like a shooting game, the archery, every time you aim at the target is what we call the parameter of interest, and every time you want to shoot right at the target, but every time there would be rare variation. For the first sample, you collect a random sample, you aim at somewhere, you aim at the target but actually hit somewhere, and for the second, you hit very close to the target parameter. Okay, so how do we estimate the population parameter? Unlike the earlier example, we know exactly what the population is with only 3 elements, 2, 4, and 6. But in general, we have a unknown distribution. For example, the random variable of interest is the IQ score of students and denoted by yi's. Okay, and we would like to estimate the parameters of the distribution, namely mu and sigma square, the mean and the variance. And we suppose that the IQ score follows a normal distribution, and our plan is to draw a random sample of size n. And a simple and natural method is to use a sample quantity to estimate its corresponding population quantity. That means we use the sample mean to estimate the population mean, and we use the sample variance to estimate the population variance. And in some other probability distribution, sometimes you would be interested in the population proportion. Okay, and denote that by P, the population proportion. For example, the proportion of students wearing glasses. Okay, the proportion of students wearing glasses. And we simply use the sample proportion to estimate the population proportion. And the sample proportion is denoted as P hat. And to look at the difference between the capital letter Y and the small letter y, the capital letter S and the small letter s. Okay, in statistics, we denote an estimator, Y bar, in capital letter. Y bar is an estimator and is a random variable. An estimator is a formula describing how you can calculate the sample mean based on a random sample of size n. Okay, now capital letter represents the random variable, that is before we actually observe the data, and the small letter y represents the observation, the observed value of y1, or the realization of y1. This is the observed value of y of the nth observation. So therefore this y bar is just a number. We call it an estimate based on a random sample. And this is just a formula telling you how to calculate the estimate based on a random sample of size n. And this is what we call an estimator before we actually make the observation. Okay, similarly for the sample variance. Okay, y bar, capital Y, is a random variable before we actually observe the data, and it is important to study the properties of the distribution of y bar. What is the properties of the distribution of y bar? For example, if you go back to the earlier example, if the population is known, if the whole population is known, then we can determine the distribution of the sample mean easily in this example. Okay, we can determine the distribution of the sample mean easily. But what about in general? Okay, so for example, this is the population with n, capital N subjects. Okay, and to draw a random sample of size n, then we will end up with y1 up to yn based on the first sample. But if ideally, if we have enough budget to repeat the experiment, we can draw a second sample, y1 up to yn, based on the second sample. And you can draw as many samples as you wish. For example, we can draw k independent samples from the populations. Okay, and repeat the sampling procedure under the same condition, of course. And for example, for the first sample, we have a random sample of size 5, and we have observations 107, 121, 98, 116, 76. Okay, we have a sample mean. We can calculate the sample mean based on this estimator. The sample mean is 103.6, and the sample variance based on this formula can also be calculated to be 315.3. Now, if we can repeat the sampling procedure under the same condition and draw a second sample of size 5, for example, we have another 5 observations, and in this case we have a sample mean of 98.4 and a sample variance of 282.3. And similarly, if we can repeat again and again and again, then we can have k different values of the sample mean and k different values of the sample variance. So therefore, the sample mean itself is a random variable subject to changes. Okay, so what is the properties of the distribution of the sample mean? Okay, we have the following theorem, and this theorem makes the normal distribution very important. The theorem says if y1 up to yn are independent random variables that follow a normal distribution, that the observations from a normal distribution with mean mu and variance sigma square, then we know that the sample mean also follows a normal distribution with mean mu and the same mean and variance sigma square over n, This is an important theorem. Okay, with mean mu and variance sigma square over n. The sigma square is the same as the population variance, but the variance of the sample mean depends on the sample size. Okay, the larger the sample size, the smaller would be the variance of the sample mean. So we have sigma square over n. Okay, so therefore, with this theorem, with this normal theorem, we can control the estimation error, namely y bar minus mu. Okay, y bar minus mu. Why we call it error? Because we use the sample mean to estimate the unknown population mean. Okay, so any deviation between the two represents error, represents the estimation error. Okay, so y bar minus mu represents the estimation error. And with the above theorem, we can control the estimation error to within a certain unit, say a unit with a high probability content, say 0.95, by adjusting the sample size. For example, this is how we write down the expression in mathematical form with a high probability content, say 0.95. 0.95 is very commonly used in statistics as high probability content. So with 0.95 probability content, the estimation error would be within a unit, minus a, between minus a and a. That is what we call within a unit. Estimation error within a unit with a high probability content. But notice that from earlier expression, we know that y bar follows a normal distribution with mean mu and variance sigma square over n if the yi's are normally distributed. Okay? So recall the Z transformation. The Z transformation is that we have y bar minus the mean of y bar, and if we divide the numerator by the square root of the variance of y bar, then we have a Z transformation. So the square root of the variance of y bar is sigma over root n, sigma over root n. If you go back to the last theorem, this is the mean of y bar. We have mu and the variance of y bar represented by sigma square over n. So a Z transformation of the random variable y bar would be y bar minus its mean, y bar minus mu, divided by the square root of sigma square over n, given in the middle. Now we have this probability argument with two inequalities. Whatever we do to any entry, we will do the same thing to other entries. For example, we divide the middle entry by sigma over root n. We do it the same thing to the first entry by dividing minus a by sigma over root n, and also on the right hand side we divide a by sigma over root n. Okay, and this transformation will have no effect on this probability argument. This probability argument will remain unchanged. But notice that what do we have in the middle? In the middle, this is equivalent to a standard normal random variable because this is just a Z transformation. Just a Z transformation, so we replace this quantity by Z, indicating that Z follows a standard normal distribution. Okay, so we have this probability argument, but that looks very familiar because we have 0.95 or the probability content 0.95. We have a standard normal random variable because we know earlier that from earlier slides, we know that with probability 0.95 based on a standard normal random variable, we have 1 minus 1.96 and 1.96. Okay, so if you go back to where we just stopped, we know with probability content 0.95, this part is just minus 1.96 and this part is just 1.96. Okay, so let's take a look at an example. Suppose the random variable y, the observation, individual observations follow a normal distribution with mean mu, unknown mean mu, and variance 15 square, and we would like to control the error to be within 2 units with probability 0.95. Okay, we would like to control the maximum error to be within 2 units with a high probability content. Okay, we can never guarantee that 100% that the error will be within 2 units. That is not possible. Okay, so we can only control the maximum error that falls below 2 with a high probability content. So we know that 0.95, based on the standard normal random variable, the quantas, the corresponding quantas would be minus 1.96 and 1.96. And from the last slide, we have A equals to 2. A equals to 2 and sigma equals to 15 divided by root n. Same here. A is the maximum error that we would like to keep, and sigma is the population standard deviation of the individual random variable y. Okay, so therefore, by matching the coefficients based on these two probability arguments, they both equals to 0.95. We match the coefficient. 1.96 equals to 2 divided by 15 divided by root n. Okay, 1.96 equals to this. And then we can solve for n equals to 216.09. Or we simply take n equals to 217. Okay, this is important, as this is just like the design of experiment. When we want to estimate the population mean with enough accuracy, we would like to control the estimation error to be within 2 units so that we can have some accurate result. How large a sample size is required? Okay, from this calculation, we need to have a random sample of 217. Then we can ensure that the estimation error will be less than 2 units with a high probability content of 0.95. And this is simply the formula. This is A times root n divided by sigma equals to 1.96. Of course, if we change the probability content to 0.90, then we would have minus 1.645 and 1.645 here. Okay, this is how we determine the sample size for the estimation of the population mean, by setting the maximum error. Okay, and for this case, we always round up the values to the next integer. Even this is 216.001, we will always round up to 217. Okay, only because if we choose 216, then this probability would be less than 0.95. But if we choose 217, then this probability would be greater than 0.95. We would choose the one that is at least 0.95, at least 0.95. Okay, but what if I don't know what the random variable is? Why? I'm not too sure whether the underlying population is normal or not. Okay, I cannot guarantee. What if the underlying population is a binary random variable, for example, supporting CY or not supporting CY, either 0 or 1. Okay, that is what we call a binomial distribution. Then what can we do? What if the underlying population is not normal? And what would be the behavior of the sample mean, the estimator of the population mean mu, when the underlying population is not normal? Okay, then we have the most important theorem in statistics, which is called the central limit theorem. It sets for any population with population mean mu, population variance sigma square, and with any sample size, we can show that the mean of the sample mean is just the population mean mu. The mean of the sample mean is just the population mean. and the variance of the sample mean is sigma squared over n. This is always true for any probability distribution, not just the normal distribution. The mean of the sample mean is just the population mean of y, and the variance of the sample mean is just sigma squared over n, where sigma squared is just the population variance of the random variable y. Okay? Now, the central limit theorem simply states that suppose the underlying population distribution of the y, the random variable y, is unknown, but we know that the mean of y is mu and the variance of y is sigma squared. So under general mild conditions, when the sample size is large, say n greater than or equal to 30, regardless of the distribution of the underlying population, it does not really matter what the underlying population is. The distribution of all possible sample means will be approximately normally distributed. That means the sampling distribution of the sample mean can be approximated by a normal distribution with mean equals to mu and variance equals to sigma squared over n, or the standard deviation of the sample means being sigma over root n. And therefore, we have the z transformation, the random variable y minus its mean, which is mu, and divided by its standard deviation, the square root of its variance. The variance of y bar is sigma squared over n, so the square root would be sigma over root n. This is a z transformation, and the central limit theorem simply sets that this transformed variable follows approximately, the dot stands for approximately, follows approximately a standard normal distribution, and that is why the normal distribution is so important. Okay, so that means y bar minus mu divided by sigma over root n. This is the z transformation, and if the sample size n is large, then this transformed variable has approximately a standard normal distribution. That is the central limit theorem. Now, an application of the central limit theorem is the following. And suppose we're interested in the population proportion, P, the proportion of Hong Kong residents who support Mr. C.Y. Leung to be the chief executive of Hong Kong. And this is the parameter of interest that one would like to estimate. And we let xi be a binary random variable with xi equals to 1 if the ith subject selected supports CY to be the chief executive, or xi equals to 0 otherwise. Now, xi equals to 1 if the ith subject selected supports CY, and xi equals to 0 if the ith subject selected does not support CY to be the chief executive. So, and define y to be the sum of the xi's. Okay, for I from 1 to n, we draw a random sample of size n from the population and ask every single individual about their response towards the supportiveness of CY. Okay, and sum of xi is just the total number of people who support CY to be the chief executive in a random sample of size n. And y is hence just the total number of people who support CY to be the chief executive. And if we take the mean of the x1 plus x2 up to xn divided by n, and the numerator here is just the sum of the n observations defined by either 0 or 1, okay, which is y. and the denominator is n, y over n. This is just what we call the sample proportion, the sample proportion of people who support CY to be the chief executive. And notice that this sample proportion can be represented in the form of a sample mean as well, x1 up to xn, the sum of x1 up to xn, and then we take the average. So the sample proportion is also in the form of a sample mean. And then we can show that the mean and the variance of the sample proportions are P, and P times 1 minus P over N. Now notice that P hat represents the sample proportion and P represents the unknown population proportion. Okay, the mean of the sample mean is the true population proportion, and the variance of the sample proportion is given by the P times 1 minus P over N. And as I mentioned earlier, that the sample proportion can also be expressed in the form of sample mean, and therefore by the central limit theorem we have P hat follows approximately a normal distribution with mean P and variance P times 1 minus P over N if N is large enough. If N is large enough. But how large is large enough? Okay, so let's go back to the earlier example. Hong Kong UPOP, the public opinion poll, okay, is about the Hong Kong U poll releases popularity figures of the chief executive and the major government officials back in 2013, if I remember correctly. Yeah, 2013. And remember, we showed this a diagram before, and those numbers in bracket, they have a random sample of 990 subjects, okay, altogether, and of which 317 support CY to be the chief executive, 502 oppose CY to be the chief executive, and 171 gave a response of don't know or hard to say, so that the three numbers add up to 990 in bracket. And also you were told how to read these numbers. 39, that means 39 people support CY and they are from the young age group and from the young age group. And 113 subjects support CY and they are from the middle age group. And 165, they support CY and they are from the old age group. So if we add up these three numbers, irrespective of age group, we have a total of 317 supporting CY. And that is the table we have. And notice that, for example, right here, what about this 32 plus or minus 3%? 32 plus or minus 3%. What is the meaning of this? I will tell you more later using this example. Now, for example, we have about 32%, 317 divided by 990 is about 0.32. The sample proportion of people who support CY to be the chief executive is 0.32, around 0.32 from this survey. Okay, just assume that the true proportion P equals to 0.32. If the true parameter is known, then we can find the probability distribution of the sample proportion based on a random sample of size 990, because the sample proportion will follow approximately a normal distribution, with mean being the true value of the population proportion and variance being P times 1 minus P over N, with N equals to 990. Now, if this is known, what about the 0.03? 0.03. Okay, suppose I would like to find the probability that a sample proportion would not deviate too far away from the true value of p, okay, with a maximum error of 0.03. Now we know that p equals to 0.32. If we plug in p equals to 0.32, in other words, then the sample proportion would fall between 0.29 and 0.35, would fall between 0.29 and 0.35. And by the z transformation, and if you plug in everything to the normal probability and make use of the Excel to solve this probability using this formula, then you can find this probability to be 0.957, 0.957. Okay, 0.957. So 0.957, 32% plus or minus 3%. What does that mean? Okay, in other words, that means if the true proportion p equals to 0.32, then we need a random sample of about n equals to 990, around 990, in order to ensure that the sample proportion would be within 0.03 unit or 3% of the true proportion with a probability of approximately 95%. Okay? But if we know the value of p equals to 0.32, we don't have to do any estimation because the one that we would like to estimate is known. So therefore, in general, p is unknown. But what if p is unknown? How can we calculate the sample size? If the true proportion p is unknown, then to calculate the sample size required, we normally assume p equals to 1/2, p equals to 1/2, such that the variance p times 1 minus p over n equals to 1 over 4n. And this is the value of the variance, which is maximized by p equals to 1/2. Notice that if p equals to 1/2, the numerator becomes 0.5 times 0.5, which is 0.25. But when p equals to 0.4, 0.4 times 0.6 is 0.24, which is smaller than 0.25. So 1/4 is the largest possible value of p times 1 minus p when p equals to 1/2. So we maximize the variance and then to calculate the sample size leading to the most conservative sample size. For example, we would like to estimate the population proportion using the sample proportion with a maximum error of 0.03. with a high probability content, say 0.95, then we can write it in this form: probability that p hat minus p would fall between minus 0.03 and 0.03 with probability content 0.95. Then we use the z transformation and to divide all the entries by the square root of the variance of p hat, which is given by p times 1 minus p over n, to all three entries. And obviously we know what this is. This is minus 1.96, this is 1.96, and this will turn into the standard normal random variable z by the central limit theorem, So similarly, we can do the mapping again by mapping this quantity to 1.96. And z follows approximately a standard normal distribution. And this z is what we call the pivotal quantity. Okay, and from previous slide, we have 0.03 divided by p over 1 minus p divided by n equals to 1.96. Now, if p is assumed known, then we know we can calculate n. But when p cannot be assumed known, as we mentioned, we simply let p equals to 1/2 to find the most conservative value of n. Assuming p equals to 0.5, we have the root n equals to times 0.03 divided by 0.5, which is the square root of 0.5 times 0.5 equals to 1.96. Then we can find root n to be 32.6667, and therefore n equals to 1067.1111. That remember that we always round up the value of n, so we take n to be 1068. The smallest value of n required is about 1068, so that the maximum error will be below 0.03, with a high probability content of 0.95. That is how we determine the sample size for estimating the population proportion. And similarly, if we can assume that p equals to 0.32 in some experiments based on past history or previous experience, p equals to 0.32, then substituting p equals to 0.32 into this equality, we can solve for n to be 30.4764 squared. And the smallest possible value of n becomes 992. So we need less observations when p is not that close to 0.5. So assuming p equals to 0.5 will give you a conservative sample size that fits that this inequality is always true. This is always true, with at least a probability of 0.95. Okay, but now, for example, if the true proportion is actually 0.32, the true proportion is actually 0.32, the probability of getting a pass from a sample, what do we mean by a pass? With a sample proportion of at least 0.5, for example. Okay, this is what we call the probability of a pass. Okay, based on a random sample of 990, if the true proportion of supportiveness is only 0.32, what is the probability of getting a pass? That means the sample proportion is greater than 0.5. Then by the central limit theorem, that is simple. This can be written as 1 minus probability of p hat less than 0.5. Okay, and by the z transformation, we have 0.5 minus its mean, which is 0.32, and divided by the square root of its variance, which is 0.32 times 1 minus 0.32 divided by n. And this probability is very, very small, 0.0000000000001. Okay, what does that mean? That means if the true proportion of supportiveness is only 0.32, the probability of getting a pass based on a random sample of 990 is almost impossible. It's impossible. These are just rough figures. These are not exact. I just make it up. Okay. Now, while if the true p equals to 1/2, actually CY is not that bad. He has been supported by half of the general public, where p equals to 1/2. Then, but what we actually observed from this sample is only 32%, a sample proportion, p hat, of 0.32. What if the true proportion of supportiveness is equals to 1/2? What is the probability of observing such an extreme observation with a p hat only 0.32? or even less than 0.32 or more extreme, we can calculate this probability to be 0.32 minus the mean divided by the square root of p times 1 minus p over n. And this probability is also extremely small. So what is the implication of this probability? Okay, because some people might argue that actually CY is not that bad. I would think that half of the general public will support CY. But based on the public opinion poll with a random sample based on 990 subjects, only 32% supported CY. And if the true value of P is indeed 1/2, the probability of getting a sample proportion as small as 0.32 is nearly impossible. So what does that mean? Okay, now this is related to the next topic on hypothesis testing. Okay, so we will come back to this later. But p hat equals to 0.32 is what we actually obtained in the sample. So what does this suggest if the polling is carried out appropriately? And we are not supposed to obtain such a result if this is true. Okay, the assumption of p equals to 1/2 should not be appropriate, but that the true value of p is likely to be much smaller than 0.5. Okay, is the implication of this probability, because this probability is calculated based on this assumption that p equals to 1/2. Okay, then we'll move on to the next topic called confidence interval estimation. Now we talk about the point estimation. Point estimation means that based on a random sample of size n, we use the sample mean to estimate the population mean, and that will provide you with a single value estimation. Y bar equals to 20, for example, or we use the sample proportion to estimate the population proportion, with the sample proportion being 0.32, okay, which only gives you a single value estimation. But that does not tell you how accurate your estimation is. Okay, so what is the confidence interval estimation? A confidence interval estimation is basically a probability statement about the unknown parameter theta, And the definition is that we would like to generate a narrow interval that will highly likely contain the true value theta with a high probability content. For example, the definition is given by let theta be the unknown parameter. A 1 minus alpha times 100% confidence interval for theta is given by theta L hat and theta U hat, okay? So that we have a high probability content, 1 minus alpha. Say, for example, alpha equals to 0.05, then we have 0.95 probability on the right-hand side, okay? So alpha is a pre-specified constant. Normally, we have a 95% with alpha equals to 0.05, or 98% with alpha equals to 0.02, or 90% with alpha equals to 0.1. So we would like to generate a probability argument such that the true value of theta is contained in falls in an interval, a narrow interval with a high probability content. Okay, and here 1 minus alpha is known as the confidence coefficient, And the idea is to generate a narrow interval so that the true value of the parameter will fall in the interval with a high probability content, 1 minus alpha. The interpretation of this confidence interval is quite difficult. It's simply interpreted as the over the collection of all 95% confidence intervals that could be constructed from repeated random samples of size n. 95% will contain the true parameter theta. I'm sure that probably you don't understand too much from this genuine interpretation, and because this is particularly difficult to be understood by the general public. So generally we use the generic interpretation. This is technically not true, but this is generally accepted by the general public, and this is conceived to be a 1 minus alpha times 100% confidence interval. Is that means that the true parameter theta will fall in this confidence interval 95% of the time. We are very confident that this confidence interval will contain the true value theta. Okay? The generic interpretation is there is a 1 minus alpha times 100% chance that the true parameter theta will fall within this confidence interval. But the genuine interpretation is, suppose we repeat the experiment 10,000 times under the same conditions. That means we draw 10,000 samples, each of size n, under the same conditions. Okay, then we, based on that formula, we can generate 10,000 confidence intervals. 10,000 confidence interval with confidence coefficient 1 minus alpha. And out of this 10,000 confidence interval, 1 minus alpha times 100% of these confidence interval will contain the true parameter theta. Okay, so don't worry too much about the genuine interpretation, but the generic interpretation would be accepted in this course, because that simply says there is a very high probability that the true value will fall within this interval. Okay, and among the Chinese, confidence interval is commonly used. Okay, because very often we use this to describe one's belief, the measure of one's belief on a certain things. Because, for example, before it actually happen, for example, you are very confident about your ability, and after the examination you would probably say that, oh, I'm 99% that I will get an A in this course. Okay, I'm 99%. And sometimes you would use, I'm 90% confident that I will fail the course. 90%. So you might have different confidence coefficient representing different measures of your belief. Okay, in Cantonese, that's something called 9成9 or 9成唔合格. Okay, so 95% confidence interval. The generic interpretation, the genuine interpretation would be the collection of all 95% confidence intervals that could be constructed from repeated random samples of size n. 95% will contain the true parameter. Okay, that means we have a population. If we can afford to draw many samples, each of size 5 under the same condition, and for each sample I can calculate a confidence interval based on the sample observations. Okay, for example, for the first observation, I can calculate the confidence interval for the mean to be 88.4 to 118.8. For the second one, that the population mean will very likely fall between 83.2 to 113.6. They are different because they were calculated based on different samples, different observations. Okay, and therefore, if we have k such samples, then we will have k confidence interval, and a 95% confidence interval simply means that 95% of these k intervals will contain the true parameter theta. But that doesn't help us much. But the generic interpretation is very useful. Okay, so let's talk about how to construct the confidence interval estimation. We let theta head be an estimator of theta, where theta is the true unknown parameter, and theta head, anything with a head that represents the estimator of the corresponding unknown parameter. And we suppose that theta hat follows approximately a normal distribution with mean theta and variance given by the variance of theta hat. Remember, the theta can be the population mean mu, which is the population mean. Okay, the parameter of interest. If theta equals to population mean mu, then theta hat becomes the sample mean y bar. Okay, and then we know that in general y bar follows a normal distribution with mean mu and variance sigma square over n. Okay, and hence suppose we stick to this general situation. By the z transformation, we have theta hat minus theta minus its mean divided by the square root of its variance. Theta hat minus theta divided by the square root of the variance of theta hat. And by the z transformation, this transformed variable follows more or less a standard normal distribution with mean 0 and variance 1. Okay, so with 1 minus alpha, we denote this quantile z alpha be the quantile such that to the right of a standard to the right of this value z alpha, the standard normal random variable will take on a value greater than this quantile with probability alpha, which is the tail probability, And for example, 1 minus alpha, consider alpha being 0.05, then we have 0.95 on the left hand side. Then you know what's going on the right hand side. We have minus 1.96 and 1.96 if alpha equals to 0.05. Okay, then by the z transformation, we plug in z given by the original transformation, theta hat minus theta divided by the square root of the variance of theta hat. Okay, and remember that whatever we do to a particular entry, we can do the same thing to all three entries such that the probability content will not be altered. So we simply multiplied all three entries by the square root of the variance of theta hat so that the left hand side becomes this. And in the middle, that cancel off, we only have theta hat minus theta. And on the right hand side, we have z alpha by 2 multiplied by the square root of the variance of theta hat. Okay, so if you recall the definition of a confidence interval that we specified earlier, okay, we would like to generate a narrow interval with two random quantities that theta will fall between the interval with a high probability content. We have this on the left hand side of the probability argument, and what we have to do on the right hand side is to isolate the unknown parameter in the middle entry of the inequality. So let's see what can we do. Okay, so we were here. We only have something left. All we have to do is to remove theta hat from the middle. How to remove theta hat in the middle entry? We simply subtract theta hat by all three entries. So we have minus theta hat minus this times square root of the variance of theta hat. And in the middle, we have minus theta left, very close. On the right hand side, subtract by theta minus theta hat, subtracted by theta hat, we have minus theta hat plus z alpha by 2 times the square root of variance of theta hat. Okay, so all we have to do is to multiply a minus 1 to all three entries. Now notice that by multiplying a negative quantity to this inequality, the direction will change. For example, 1 is less than 2. 1 is less than 2. If we multiply a minus 1 to the inequality, we have minus 1 and minus 2, but minus 1 is greater than minus 2. Okay, so therefore the sign will change. So we multiply a negative 1 here, we have theta hat plus z alpha by 2 times square root of the variance of theta hat. That would be on the side. And multiplying this by minus 1, we have theta hat minus z alpha by 2 times the square root of variance of theta hat that would move to this side. And then we have the high probability content, the unknown parameter isolated in the center, in the middle entry of this probability argument. So it is easy to see that this would be the theta L hat, the lower limit of the confidence interval, and the upper limit of the confidence interval. So in the cases with normal distribution, a 1 minus alpha times 100% confidence interval for theta is thus given by theta hat on the left-hand side is minus z alpha by 2 times the square root of the variance of theta hat. And on the right-hand side, this is theta hat plus z alpha by 2 times the square root of the variance of theta hat. And suppose the variable of interest is y, where y is known to follow a normal distribution with mean mu and variance sigma square. And then we know that y bar follows a normal distribution with mean mu variance sigma square over n. So therefore, to construct a 95% confidence interval for the unknown parameter mu, the population mean, okay, we let alpha equals to 0.05 for 95%. So therefore, z alpha by 2 is 1.96, the magic number that this quantile is provided in the examination. Okay, 1.96. Now, of course, if alpha equals to 0.1, that means we would like to have 5% probability on the left tail and 5% on the right tail. Then this quantile becomes 1.645. Okay, so a 95% confidence interval for the population mean mu is thus given by when theta equals to mean, the population mean mu, then theta hat becomes the sample mean. Okay, y bar plus or minus 95%, 1.96, multiplied by the square root of the variance of y bar. The variance of y bar is given by sigma square over n. Taking the square root, that becomes sigma over root n. Okay, so this is the general formula for the population mean mu, and sigma would have to be known. For example, y followed a normal distribution with mean mu and variance 15 square, with n equals to 100 observations and the sample mean y bar equals to 100. A 95% confidence interval for the population mean is thus given by y bar plus or minus 1.96 times sigma over root n. Root n is 10, sigma is 15, and the variance is 15 squared. Standard deviation is 15. So we have 100 plus or minus 2.94, giving you a confidence interval for mu is given by 97.06 and 102.94. And that will give you a more accurate estimate because you know the error, the size of the error based on this confidence interval, instead of knowing that the estimate is 100 but you don't know the size of the error. Okay, that is the confidence interval for the population mean. In this course, we always assume that the population variance is known. The population variance is known. Okay, which is 15 square in this particular example. What about for the population proportion? In this course, we will consider two confidence intervals, one for the population mean and the other one for the population proportion. Remember that the population proportion can also be expressed in the form of the mean, and the sample mean can also be expressed in the form of a sample mean. And by the virtue of the central limit theorem, we know that p hat follows approximately a normal distribution with mean p and variance p times 1 minus p over n. So by the same token, this is the general formula. Okay, theta, the unknown parameter of interest, is the population proportion. So theta hat becomes the sample proportion. Theta hat is just the sample proportion. Plus or minus z alpha by 2. Alpha equals to 0.05, then we have 1.96, for example. And what about the variance of theta hat? The variance of p hat is known to be p times 1 minus p over n. But here, the variance involves the unknown parameter p that we are estimating. So therefore, there is no way we can calculate the confidence interval for the population proportion p. Okay, so what can we do? A simple convention is to approximate the true value p in the variance term by the sample proportion to give p hat plus or minus 1.96 times the square root of p hat times 1 minus p hat over n. And this is the confidence interval for the population proportion when the sample size n is large enough. Okay? And therefore, if you go back to the Hong Kong UPOP example of CY, now P hat equals to 0.32 based on a random sample of size 990. A 95% confidence interval for the true proportion of supportiveness for CY is given by P hat plus or minus 1.96 because of the 95% confidence interval, and multiplied by the square root of p hat times 1 minus p hat over n. And everything is very simple, and just plug in the estimate. And that's why we have 0.32 plus or minus 0.029, where they round that up to 0.03 because they are actually showing a 95% confidence interval for the true proportion of supportiveness for CY in that particular example, plus or minus 0.03. And to be precise, the true value of P should fall between 0.2909 and 0.3491. Also, a 90% confidence interval for P is given by everything is exactly the same except that this magic number will change to 1.645. Okay, with a smaller confidence we have a slightly narrower interval. Okay, a wider interval will have a wider interval we have a higher confidence. Can we have 100% confidence interval? Yes, you can have 100% confidence interval, but the interval would become minus infinity to infinity, or in this case from 0 to 1. Okay, so 100% in statistics is meaningless because we study the randomness. But which is narrower than the 95% confidence interval? A 90% confidence interval is narrower because the accuracy required is less. And I'll stop here for this, and we will come back to the next topic on hypothesis testing. Thank you very much.